Welcome to Empowered Learning. This video will be about one-sided limits. We'll talk about the purpose of one-sided limits, how to look at and interpret one-sided limits, and we're going to look at some examples of how to evaluate functions that are known for being one-sided. Sometimes we're interested in the behavior of a function at a particular x value a from either only the left side of that x value a or only from the right side. This is especially useful in the following situations. Now, the functions that I have here are situations where either the function itself is one-sided or there's some kind of discontinuity in the function, and I want to be able to study one side of where that discontinuity is, okay? And that's really the whole point and purpose of a one-sided limit. Now, what is a two-sided limit? Let's talk about that. If you've watched my video, the primer on limits, or the one where I talk about evaluating limits empirically by using graphs and graphing calculators, or if you've watched my one on limit laws, then you'll see here that anytime we talk about the limit as x approaches a of some function f of x, and it is equal to some real number L here, we'll say, when we say limit as x approaches a, what we really mean limit as x approaches a from both the left and the right, okay? And so you see here that we don't have, let's say, this plus here in the exponent for this case, or a minus here in the exponent for this case here. So we're looking at the behavior coming from both sides of that particular x value. When we want to specifically just focus on either the right side, we do this plus here in the exponent for the x value that we're approaching. If we want to do it from the left, we do a minus in the exponent for the number that we're trying to approach. And so this, by definition, is a two-sided limit, whereas limits like these are one-sided limits. So now that we have that cleared up, let's look at situations where one-sided limits would actually make sense for us to even consider. So, of course, one consideration is when we're at the end of a domain of a function. So, for instance, square root of x, if we're looking from the right going to the left, we see that it abruptly ends at x equals 0, okay? And our function is going to be undefined for all of this over here. So for any value of x that is less than 0, it's undefined. We don't have anything there. So there's no behavior to study, okay? So again, it only makes sense for us to look at the behavior of this function only coming from the right. Because if I was to look at, let's say, limit as x approaches 0 from the left, that didn't quite write the way I wanted it to there. So 0 from the left of this, I would have to answer this as does not exist because, again, there is nothing here for me to evaluate the behavior of, okay? Now, another instance is where we have a vertical asymptote in our graph, okay? And we can see for the function 1 divided by x plus 8, we have a vertical asymptote here at the vertical line x equals -8. In that instance, notice that a vertical asymptote is a type of discontinuity where your function either tries to climb above the wall, as I like to say, or tries to dig below the wall. Now, if I only wanted to study the behavior of this function coming from the left side of x equals -8, and I don't know why this says 0 here, but this should be -8 right there. Then in this case, we would see that this particular limit here, if we approached -8 coming from the left side, we would evaluate that and our limit would go towards negative infinity because our graph gets more and more negative the closer and closer it gets to -8 coming from this side. Okay. Now, of course, if we did the same thing, limit as x approaches -8 coming from the right, as we get closer to -8 coming from the right, my graph goes up. So that means my y values are getting more and more positive. So it'll be infinity in that case. And so we use one-sided limits to actually help us to be able to describe the behavior of a function in a formal perspective, meaning using limits, so that later on in a first year calculus course, we would give you a problem like, hey, here's this function and it has all these properties. And some of the properties that we would give to you is to say that, hey, the limit of this function as x approaches -8 from the left goes to negative infinity. Okay. Well, that's telling you right there, hey, guess what? It looks like I have a vertical asymptote at x equals -8, just because of that one statement there. And so by knowing the properties of these functions through limits and other things that we'll talk about in later videos, you'll see how we can actually piece together what a possible function f of x could look like solely based upon statements like the limit of the function is whatever. Okay. All right, so we've talked about the in the domain case. We've talked about the vertical asymptote case. Let's talk about jump discontinuities. Okay, and so this particular function here, absolute value of something divided by the same thing that you took the absolute value of, is a common function that we look at to be able to display why we actually use one-sided limits. So here we know that absolute value of x minus 1 divided by x minus 1, that function just looks like what you see here. Okay, and so in looking at that, we see that the limit or the behavior of this function as x approaches 1 from the right will be approaching a y value of 1 in this case. But if I was to change this now from a plus to a minus here in the exponent, and I looked at the behavior of this function as x approaches 1 from the left, then of course the y value would be approaching -1 in that case. Okay. So again, end of domain, vertical asymptotes, jump discontinuities, or just discontinuities in general, are all situations where we want to use one-sided limits to give us a better way to describe the behavior of the function that we're dealing with. Okay. Now, again, in the notes here, I've already mentioned this. Whenever we have the negative in the exponent here as x approaches a, then that means we're just evaluating the limit from the left. Of course, if we have the plus in the exponent, we're evaluating the limit from the right. Now, the next things I'm going to show you are the formal definitions of what a left-hand limit and what a right-hand limit look like. Okay, I'm not going to spend a whole lot of time on it, only because in reality we really don't care about this if we're like in our first year calculus course and we're just trying to get a basic idea of what limits are and how to evaluate them. These definitions become important if we're actually trying to evaluate the precise definition of a limit. Okay. And again, all this really says is this notation just means that we're looking at a left-hand limit of f of x as x approaches a, only from the left. And we know from a precise, or I should say informally precise situation, that we know that the limit of this function as x approaches a from the left is going to equal to this real number if we can make the values of f of x. So when you see this, think of y values. If we can make the y values arbitrarily close to this limit value L here, by taking x to be sufficiently close to a, where x is always going to be less than a. Okay. Now, all that means is this. If I know that my limit is L and my y values are like half a unit out, then that may mean here for my corresponding x values, I may be 0.2 of a unit out from that. And of course, the x values that I'm choosing here are always going to be smaller than a because I'm approaching a from the left. Okay. Now, the right-hand limit, it's the same concept. The only thing that's different now is that as our y values approach L, our x values will be approaching A. In this case, we're approaching it from the right. So that means, these values x here are going to be larger than A. Now, if we talk about infinite limits, these are limits where the limit itself ends up either equaling plus or minus infinity, or we are taking the limit of a function as x approaches plus or minus infinity. Okay. And so when we talk about one-sided limits, we have to talk about infinite limits naturally, because of the fact that a lot of times, especially in the vertical asymptote case, we're having to say that the limit of the function is either plus or minus infinity. Okay. Now, infinite limits usually come as a result of dealing with functions that have vertical asymptotes. Like I mentioned before, the most common elementary functions that could possess vertical asymptotes are rational functions, logarithmic functions, and trigonometric functions. Okay. And so in saying what I just said there, I want to make sure that you understand that when we go through this whole process of trying to learn limits, a lot of times I'll have students think that, hey, we're learning how to computationally evaluate limits. So that means that I don't have to necessarily know what all these graphs look like anymore because I can just evaluate the limit algebraically. Okay. And that could be nothing further from the truth. Okay. There is no substitute for knowing what your basic algebraic and trigonometric function graphs look like. Okay. In my opinion, you must know these. You must have these cataloged in the back of your head, because as you start to evaluate more difficult or more complex limits, you're going to see that at some point in time in evaluating those types of limits, you're just going to have to know what the graph looks like. Okay. To be able to know its behavior. And there's really no substitute for it. Okay. And I want to make sure that you know that and that you understand that, because having that skill set of being able to know, hey, I need to evaluate what the limit of tangent is as x approaches pi over 2 from the left, and you know what that actual answer is. Okay. Being able to at least produce the graph in your mind and know what that answer is relatively quickly is powerful when in evaluating limits. It's so powerful. So I want to make sure that I emphasize that, so that if you know that you're a little bit shaky on knowing those basic graphs, spend some time, learn it, because it really will help you as you go on throughout your career in taking calculus. All right, so back to the infinite limits here. All I want to say is that if we're talking about a positive infinite limit, then that means that we're taking the limit of some function as x approaches a from both the left and the right, and we end up answering it with a positive infinity. Okay, and of course, we give the formal definition here. All it's basically saying here is that as x approaches some number from both the left and the right, the y values will get larger and larger and larger as x gets closer and closer to this value a. Okay, that's essentially all it says. For negative limit, same thing. As x approaches some value a, my y values are going to get more and more negative. And of course, the graph of this particular function here, -1 divided by x plus 3 quantity cubed, is a good example of that. Now, for a vertical asymptote, one of the reasons why we know whenever we look at the limit of a function, we know that that's describing a vertical asymptote is if that limit looks like one of these 6 outcomes here, okay? So if we are evaluating the limit of a function as x approaches some specific real number value, and we answer with either positive or negative infinity, we know we have a vertical asymptote in our graph. Okay, 100% of the time, that is true. Okay. Now the question is are we talking about the left side behavior of that function at that vertical asymptote, the right-hand side behavior of that function at the vertical asymptote, or are we talking about both sides simultaneously? Okay, and that is where our one-sided limits come into play to be able to make that distinction. So if we look here, I'm going to erase this so that you can see everything clearly here. If we look at these first two, and I'm going to number them here. If we look at 1 and 2 here, sorry. Let's try that again. So if we look at 1 and 2, 1 and 2 are the situation that looks a lot like this example here, where we see that the behavior of this particular function as x approaches -3 from both the left and the right, it's going to go to negative infinity. And I don't know why that doesn't say negative infinity there, so I'll put it there. So here we see that the behavior of my function coming from both the left and right both go to negative infinity. Okay, so that would be like case number 2. If I was to look at this particular function and evaluate its limit, this would be like case number 1, where the function goes up both on the left and right as x approaches or gets closer to 1. These next two, 3 and 4, are what it looks like whenever we study a vertical asymptote only on its left side. Okay. And I'm going to go back here. So if we were considering this function and I wanted to figure out what is the vertical asymptote, what is the behavior of this function only on the left side of the vertical asymptote, we're talking about something that looks like this. If we want to study it only on the right, we're talking about something that looks like this. Okay. And of course, for this particular function, as x approaches -8 from the left, it goes to negative infinity. As x approaches -8 only from the right, it goes to positive infinity. All right, so let's go back here. Now, of course, 5 and 6, this is the case where, of course, we're only looking at the behavior from the right-hand side, okay? And so those same two examples that I showed you here, whenever I was on the right side of the vertical asymptote, that is what those two cases mean, okay? Now, again, I make this point here, and I know I've made it in earlier, and I've made it in other videos as well. So we answer, whenever we have a situation where we answer our limit of a function as x approaches some specific real number x value, and we have to answer it with plus or minus infinity, our limit technically does not exist, okay? However, in these situations, we do not write D in E, okay, meaning does not exist. We actually write the plus or the minus infinity, okay? And we do that because, remember, the purpose of a limit is to describe behavior, okay? The limit is an operator asking you to figure out the behavior of this particular function. Positive and negative infinity, especially for vertical asymptotes, is a better description of behavior than D and E is, okay? And we really reserve D and E, or the true does not exist, for situations like what I showed you earlier, and I'm going to go back to it. So for situations like here, where the actual behavior of our function as x approaches some value from the left approaches a different y value than it does from the right. So again, here, as x approaches 1 from the left, the y value is approaching -1. If we approach x equals 1 from the right, it approaches +1. And since -1, +1 aren't the same, we know that the behavior of this function coming from the left and right aren't the same, and thus we have the does not exist or D and E case. Okay. All right. So what we're going to do now is actually evaluate some limits here. Some of them will be one-sided, some of them won't be. Now, in my opinion, the best way to evaluate these limits is just to know what the graphs look like. Okay? And for these examples, I'm going to sketch what the graph should look like. And from that, we're just going to evaluate the limit. And you're going to see it's going to be relatively simple to do. So let's look at the first 3 examples here, since they're all the same function. And notice here, all this is just a log base 5 function that's been shifted over 2 units to the right. So if I was to draw a graph of that, a vertical asymptote here at x equals 2. And our basic logarithm function would look something like this. And of course, this would always cross the x-axis 1 unit from where the vertical asymptote is. So now that I have a graph of what log base 5 of x minus 2 looks like, I can literally just look at this graph and answer questions. So for A, this is asking what is the limit or what is the behavior of this function as x approaches 2 from both the right and the left of x equals 2. Okay. Now, the answer to this question is just does not exist. Why is that? Here, because we don't have a plus or a minus in the exponent here, we're looking at this as a two-sided limit, meaning we're trying to study behavior from both the left and the right of our value x equals 2. Since we don't have anything here, meaning our graph does not exist for values of x that are 2 or lower, there's nothing to study. So although the behavior from the right may be going down to -infinity, the behavior from the left, there's nothing there. Okay, so we can't even put a plus or minus infinity there because there's literally nothing here to evaluate. Okay, now for example B, this will also be does not exist because again I'm asking for the behavior of this function as x approaches 2 coming from the left. Again, there is nothing there. So since there's nothing there, can't evaluate it. Okay. Now, same function, but we're looking at the behavior of the function from the right. This will be -infinity because as x approaches 2 from the right, the y values for this function get lower and lower and lower, or more negative, more negative, more negative. Okay. And so that is how we know, how we use one-sided limits to be able to properly describe the behavior of this particular function. Now, if I had these limits here, and let's say I just said this was f of x, and I didn't even say it was log base 5 of x minus 2 here. Just by looking at these 3 limits here, I would know that my function had a vertical asymptote at x equals 2, and that my graph would be going down to -infinity the closer and closer it got to x equals 2. And I would know for all values of x that are 2 and lower, the graph or the function would not exist. I could tell all that just from those limits there. Okay. All right, let's move forward here. So for our next example, we want to graph what 1 divided by x plus 3 cubed is. Okay. Now, notice that 1 divided by x plus 3 cubed is going to act a lot like 1 over x plus 3. The difference is with the cubed, and I'll go ahead and draw what this looks like here. So the difference here, let me finish drawing it first. So look more like this. And I also have a horizontal asymptote here at y equals 0. So the only difference in between what I have here and here is that this piece of the graph is going to rise higher, faster, and this graph is going to decrease down and bend like this faster. That's the only thing that's really different about it, okay? So if I'm looking at the graph of this function here and I'm saying, hey, let's find the behavior of this function as x approaches -3 from the left, okay? So as x approaches -3 from the left, my y values are getting more and more and more negative. So I would answer this as a negative infinity, okay? All right, so let's look at example E, different function. And so for this one, this would be square root of x plus 4. So I'm going to erase this function here and replace it with square root of x plus 4. All right, so we now have our graph of what square root of x plus 4 looks like. It is just the square root of x function shifted 4 units to the left. So now if we looked at this function and said, let's study the behavior of it as x approaches -4 from the left. Well, from the left of x equals -4 is all over here. And notice, since our graph does not even exist for values of x that are less than -4, we have nothing to evaluate the behavior of. So we would say that this is a does not exist case. All right, so looking at our next example, we have square root of x minus 5 minus 2. So again, this is a graph of square root of x, but this minus 5 means that we're shifted over to the right 5 units. And this minus 2 here means that we're also shifted down vertically 2 units. So if we draw a function that kind of mimics that, that graph would look something like this. Okay. And so now what we're being asked is to study the behavior of this function that we've drawn a graph for as x approaches 5 from the right. Okay. So that means we're coming from the right here, and we see as x gets closer and closer to 5 here, the points, their y values are getting closer and closer to -2, okay? All right, so for our last 2 examples here, we'll use the same graph. And this is the graph of -1 divided by x to the 6. And if you think about this, since this is an even exponent here, this is going to look a lot like 1 over x squared. And 1 over x squared looks like this, but since it's negative, it's actually going to go down and look more like that. So our graph here, we're going to have vertical asymptote at x equals 0. And our graph's just going to basically look like this. And here we also have a horizontal asymptote at y equals 0 here. Now, if we're studying the behavior of this particular function that we've just drawn as x approaches 0, remember, here we're saying that we're studying the behavior from both the left and the right. And we see that our graph here, both from the left and right of x equals 0, goes down to -infinity. So we're going to answer this as -infinity. Now, if both sides of the graph go down to -infinity as x approaches 0, then of course the left side is also going to do the same thing. So we're just looking at this side here, okay? All right, So this concludes the lesson on one-sided limits along with infinite limits. And I hope this helped clear things up for you. And again, I want to stress this again. Please take the time to learn the graphs of your basic algebraic and trigonometric functions if you have not done so and you're taking a calculus course, because it really does help in allowing you to have some intuition on what's going on whenever you evaluate limits.